Welcome to The Explainer. So today, we're unpacking one of the most fascinating and totally invisible mechanical feats happening in your pocket, literally right this second. We're talking about LTE Uplink power control. If you've ever found yourself wondering how your phone just magically keeps a seamless connection while you're moving through a super crowded city, well, it all comes down to a high-speed game of Goldilocks. The network is constantly telling your phone, hey, don't be too loud, but also don't be too quiet. Let's get into exactly how it finds that just right sweet spot. Really think about it. When you're standing right next to a cell tower, your phone barely needs to whisper for the data to get through. But if you walk a mile away and maybe step inside a thick concrete building, your phone absolutely has to shout. So, the fundamental problem we're looking at is this. How exactly does the network manage the volume of thousands of devices all at once, keeping your connection completely stable without letting you drown out everyone else's signal? To understand how engineers actually pulled this off, here is our roadmap for today. First, the LTE power problem. Second, open loop power control. Third, balancing capacity and coverage. Fourth, closed loop power control. And finally, number 5, fine-tuning the network. All right, section 1, the LTE power problem. Let's quickly establish exactly what makes LTE so wildly different from the older networks. Okay, let's dive into this. Back in the 3G days, which is WCDMA, power itself was actually the main resource. But LTE totally changed the game. LTE uses orthogonal frequencies, which basically means it separates users into distinct lanes. That essentially wipes out interference from phones connected to your exact same tower. So the new main resource became physical resource blocks, or PRBs. And because users in the same cell aren't stepping on each other's toes anymore, a brand new ultimate enemy emerged: intercell interference. That's the noise you accidentally cause to neighboring cell towers. And that brings us right to the Goldilocks problem. Think of it like a giant dinner party with a bunch of different tables. If you shout to be heard at your table, you totally ruin the conversation for the table next to you. And honestly, nobody likes that guy. In LTE, if users transmit with too high of a power, cell edge users in neighboring cells just get completely jammed. But on the flip side, if you transmit with too low a power, perfectly good connections will just drop, which starves the whole network of its efficiency. So how do we fix it? That brings us to section 2, open loop power control. Take a look at this. This is the master equation for calculating a device's transmission power, otherwise known as PUSCH power. Now, I know it looks a bit complex, but it basically splits into two heroes. That large orange box, that represents the open loop foundation. It calculates power based on cell-wide rules and path loss, which is basically just your distance from the tower. And then, that smaller purple box at the end is the closed loop part. That acts as an active traffic cop, making tiny real-time corrections. Let's focus in on that open loop foundation first. Within that open loop formula, the very first major variable engineers configure is P0. You can really think of P0 as the baseline volume requirement set by the cell tower. It defines the target receiver sensitivity. So by adjusting P0, engineers are essentially deciding the default baseline power that every device in that specific cell should aim for before even accounting for how far away they are. Then we have the second crucial open loop variable, alpha. Alpha is the fractional path loss compensation factor. Basically, as you walk away from the cell tower, your signal gets weaker, right? That's path loss. Alpha tells your phone exactly how aggressively it should increase its transmission power to compensate for that loss. It dictates the slope of the power curve. And honestly, setting that slope is where network engineers really earn their paychecks. Let's move to section 3, balancing capacity and coverage. This trade-off is a seriously delicate balancing act, and this illustrates perfectly why that is. If engineers set alpha to 0, there's absolutely no compensation. The result? Great capacity for the people right near the tower, but miserable, practically unusable coverage for anyone at the edge of the cell. Now, if they set alpha to 1, it provides full compensation. Phones at the edge are shouting at maximum volume, which gives them great coverage, but it causes massive interference and drags down the entire network's capacity. So here's the key takeaway. Engineers rely on fractional compensation. By setting alpha somewhere between 0.4 and 0.9, often right around 0.8 for most scenarios, the network hits this beautiful compromise. It's a fractional power control scheme that keeps the center of the cell highly efficient while still giving users at the outer edges just enough power to maintain a solid connection without ruining the neighborhood for everyone else. But as we all know, a baseline rule just isn't enough for the messy real world. That takes us to Section 4, closed loop power control. While open loop sets a great baseline using average distances, the real world is, well, unpredictable. You might suddenly walk behind a thick concrete pillar. That's called sudden shadowing. Open loop is just way too slow to fix that. So we bring in closed loop power control, or CLPC. This is a highly reactive system. It overcomes sudden drops in signal quality. It actually helps minimize your phone's battery consumption by lowering power the instant it's not needed, and it actively manages real-time signal conditions by constantly communicating back and forth with the tower. Now, what's really interesting about this is the exact cheat sheet the cell tower uses to manage your phone. The tower measures two things: signal to interference plus noise ratio, or SINR, which is your signal quality, and received signal strength indicator, or RSSI, which is your raw signal strength. It plots them on this 3x3 matrix. Depending on exactly where your phone lands on this grid, the network sends a tiny command to nudge your transmit power. It might say, hey, increase by 1 decibel, or decrease by 1 decibel, or if conditions are terrible, increase by 3 decibels. And all of these little nudges build toward one ultimate goal. That's center square. If you look at square number 5 on that matrix, the command is 0 decibels. That is the target performance. It means your device's power is perfectly, flawlessly matched to the network sweet spot. The entire goal of these continuous upward and downward nudges is to push every single active phone right into that center square. So they're running purely on that highly optimized open loop baseline we talked about earlier. And the speed at which this happens is just incredible. The network measures your filtered signal metrics, compares them against the 3x3 matrix, and sends a transmit power control, or TPC, command to your phone. And because this is a closed loop, it happens continuously. It's constantly adjusting your phone's output power millisecond by millisecond as you move through your environment, keeping that connection totally stable. Finally, let's see how engineers tie all of this together. Section 5, fine-tuning the network. So, after running massive simulations for heavy network loads, engineers discovered a golden rule for optimization. To achieve the absolute perfect 50-50 balance between network capacity and cell edge coverage, the optimum baseline power, that's our P0, should be set to -100 multiplied by our alpha slope. This simple, elegant formula serves as a vital anchor point. It allows engineers to confidently configure the network's baseline before that real-time closed-loop traffic cop even needs to step in.
It's truly a marvel of modern engineering, isn't it? You have this massive baseline equation balancing thousands of users, paired up with a real-time matrix making split-second corrections. So I'll leave you with this thought. Next time you're streaming a video while riding in a car or walking through a dense city, think about that invisible engine in your pocket. How many times per second is the network mathematically tweaking your phone's power just to keep that video playing without a single hitch? Thanks for joining me on this explainer, and keep exploring the incredible technology all around us.